Hey physics kids, Campbell here. In our second video on optics, we're going to talk about one of my favorite optics topics, thin film interference. Thin film interference is another example of the wave nature of light. So what is it? Well, anytime we have light and it hits a boundary of different refractive index, different density, right, it's going to reflect, just like waves on a string reflect anytime they hit a medium that has different density. And so, for example, let's say I have glass, right? I have glass and maybe there's air on one side of the glass, right? And here's my glass layer. And then I have air on the other side, right? Now I have changes in refractive index between each of these layers. And so not only is light reflected off that first boundary where it encounters that higher density material, but some of it penetrates through, right? Because we see the light on the outside too. And so that travels through the glass, and then it hits the next boundary where the density changes. I go from higher density glass to lower density air, and the wave reflects again. Well, if it comes out and it has enough intensity, it can interfere with the initial reflected wave. And this is thin film interference. Now, in order for this to happen, that film, so like the glass, would have to be very, very thin. So a few wavelengths thick or less, right? And we're talking about in the nanometer range. So light will reflect from both the bottom and the top layer, and causing, when it comes out, we get this interference. But like I said, it has to be very, very thin, because if it's not, then the reflected wave, the second reflected wave, isn't going to have enough intensity to interfere, because remember, some of it's going to get absorbed by that higher density medium. Good examples of that are like soap bubbles, right? You blow bubbles outside and you see pretty rainbow colors, or if you ever see some gas spilled on like some concrete and it's raining, you can see pretty colors. So what's going on here? Well, we have light that comes in, right, and it hits this film, this different density medium, and I get reflection off of the two interfaces. So I have, here's my ray 1 reflecting. Some of it penetrates through and refracts, but when it hits this different density medium or boundary again, I'm going to get some reflection off of that boundary. And of course, some of it still penetrates through. Now, if this happens, so here's my incoming wave. If when this ray 1, I'll call it, reflects, and this, we'll call this ray 2 reflects, if they are lined up, so those wavelengths, the peaks are lined up, the troughs are lined up, then I get constructive interference and I see the light. I see the light because my wavelengths are lined up. But if my waves reflect and now peaks and troughs are lined up together, right? They cancel each other out because waves superimpose on each other. And so I don't see it anymore. It's off by a half a wavelength. That's called destructive interference. So they completely cancel out if they're completely off. So if they're off by a half a wavelength. Now the things that affect this, being in and out of phase, is one, ray 2 here, my second ray, right, has to travel farther, right? It has to travel through the thickness of the film and back. So we say that it travels 2T. 1T, 2T. So it travels farther than ray 1. So that's one thing. So that thickness is important. The second thing that's going on is the density difference between each phase, ray here and refractive index 1, or my air, maybe, and here too. Those differences will also affect how the ray reflects. It could reflect in phase, so it stay the same, or it could flip and invert the ray. Now, if you remember back to waves last year, we talked about mechanical waves, like waves on a string. And remember that if we sent waves on a string, and we did this actually with slinkies, and it hit a fixed end, which is kind of like a higher density medium, then the wave would reflect inverted. But if we sent our ray down, or a wave down on our string, and it had a free end or a less dense, the wave would reflect upright. Well, the same thing happens with light. So cool. So if light is reflecting off a higher index of refraction. Remember, that means it's more dense, harder to move. And so what happens is we get this phase shift or this wave inversion. Anytime light's coming from air and it reflects off anything like glass, water, oil, it will undergo this phase shift and I'll get off by half a wavelength because it's inverted now. But if light travels from a higher density medium into a lower density medium, then no phase shift occurs because it's easier to move, so it stays upright. So then no phase shift. So like if light is traveling from oil into air, then no phase shift occurs. So the way I like to say it is if it goes high to low, no. Low to high, yes. Phase shift. High to low, no. All right. So let's look at how do we solve problems for thin film interference, right? So we need to determine, is there a phase change for each wave when it hits its boundary? And then we have to add our extra distance of the thickness of the film to ray 2. So the way I like to set this up is like this. I say ray 1 either flips or no flip. Flip or no flip. High to low, no flip. Low to high, yes flip. And so if it flips, I assign it a half, right? Because now it's out of phase by a half. If it doesn't flip, so high to low, no flip, then I just give it a 0. So ray 1 only reflects. It doesn't go an extra distance, so that's all I have to worry about, flip or no flip. Ray 2, right, when it hits its boundary between N1 here and N2, right, I have to look at the reflection. So I have to look at, is it low to high, in which case it flips and I give it a half, or is it high to low, no, and then I give it a 0. And then to that, we have to add this extra distance. And we have to add this extra distance in terms of the wavelength in the film, right? It's traveling through the thickness of the film. And remember that the wavelength changes. It gets shorter when it moves through a higher density medium. Longer if it's a less dense medium. So I have to add to that 2 times t, which is the thickness of the film, divided by the wavelength in the film. Now remember this equation from the first video, wavelength in any film is the wavelength in air or a vacuum divided by the refractive index of the film. So then what I do is I subtract those. I take the absolute value of the difference between what I have for ray 2 and ray 1, and if I end up with some whole number or 0, 0 is a whole number, I get constructive interference. But if I take the difference between ray 2 and ray 1 and I get some half or some multiple of a half, then I get destructive interference. So let's see what this means. Let's try something. All right, constructive or destructive. So I have light coming through air, hitting an oil film with a refractive of 1.5, hitting a boundary in water. So I've got oil floating on water here. Now the thickness of my oil film is 1/4 of the wavelength of this red light. Oh, it's red light. In oil. Does that matter? I don't know. Okay, so we have to ask ourselves, ray 1, flip or no flip, so phase change or not. Ray 2, flip or no flip, so phase change or not. And then how much farther? So this is what my equations would look like. So ray 1, it goes low to high. So low to high, yes, it flips. So I give ray 1 a half. Ray 2, does ray 2 flip? Well, it goes high to low, so high to low, no. So no flip, so I give that a 0, and then I have to add 2 times the thickness divided by the wavelength in the oil. Now, it told me that the thickness of this was 1/4 of the wavelength of oil. So for T, here, I'm going to put 1/4 lambda in oil. All right, so I substitute that in for T. Notice that my oils cancel. And so I have 0 plus 2 times 1/4, right, which would just be a half. All right, so now I'm going to subtract take the absolute value of ray 2 minus ray 1, and I get 0. Well, that's a whole number, so it's constructive. So because I have a phase shift at the first one, no phase shift in the second one, and my total travel is 1/2 of the wavelength of the oil, then I get constructive interference. Now, if we had switched this and maybe had a little thicker, so maybe it was a half of a wavelength in the oil, right? If this was a half, then this would end up with a whole number, and I would end up being off by a half, and then it would be destructive. But in this case, constructive. All right, let's try another one. If you buy glasses that have anti-reflective coatings, what they've done is they've applied a thin coating. The refractive index of that coating is 1.38 on top of your glasses. So glass refractive index, this case is 1.52. And the thickness of the coating is important, right? If it's a 1/4 the wavelength in film, hopefully when we do our math, we're going to end up with a difference between ray 2 and ray 1 to be some multiple of a half. All right, let's do this. So again, remember we have to ask ourselves, ray 1, phase change or not, flip or no flip, ray 2, flip or no flip, and then how much farther. So ray 1, do we have a flip or no flip? Well, we go from low to high, right? Anytime it's air, ray 1 is going to be a half. Here, I go from low to high again, so in this case, I do have a flip. I have to add 2t over lambda in the film. All right, so my t value is 1/4 of the wavelength in film, so I'm going to plug that in here. And now I'm going to take a half, and I'm going to add it to 2 times 1/4, which would be a half. So a half plus a half is 1. So now when I subtract them, I get 1 for ray 2 minus a half from ray 1, and I get a half. Whew, that's good. It's anti-reflective. All right, you try this one. I have blue light, and I have some numbers here. Is the interference destructive, constructive, or neither? See if you can figure this out. I gave you numbers this time, so you can plug some in. Pause the video, see if you can get it right. Well, let's take a look. So hopefully you said that ray 1 flipped, and I'm going to use gammas instead of ray 1. Sorry. So I get reflection at the air film interface. That's a flip, right? Low to high, flip. But my second reflection is a high to low, so that's no. And then I add 2t times the wavelength in the glass. So that means I take 2 times the thickness they provided, 167, and I divide by the wavelength in the glass. So take your 500, that's blue light, divide by the glass, the refractive index of glass. And when you do that, you get 1. It's pretty much close to 1. So 1/2 minus, or 1 minus 1/2 is a half, which means hopefully you said destructive. Now, if you're a equation kind of person, the book has some equations, and this is what they look like. But I'm not an equation kind of person for this. In fact, I remember in college when I took physics, I went to ask the TA, I'm like, how on earth do you do these thin film things? I totally do not get it. I'm like, which equation am I supposed to use? I mean, is this constructive or destructive? Is it 1 or 2 phase changes? Ah, I don't get it. And he's like, I don't use equations. So he taught me how not to, which is how I taught you. Hopefully you will go with my way. Because I'm not going to, if you ask me which equation to use, I'm going to say, I don't know. Now, what's really cool, if you think about anytime you see thin film interference, you usually see if you're outside, right? Because outside you have sunlight, which has all of the visible spectrum in it. You see different colors, like in your soap films, and in like if there's a gas spill. It's because different locations have different thicknesses, and if they have different thicknesses, they reinforce different colors, right? Because different colors of light have different wavelengths, right? Red has a longer wavelength than, say, purple, which has a shorter wavelength, right? It's higher energy. This is also the case, not exactly thin film interference, but definitely light wave interference is like peacock feathers or butterfly wings. They have like ridges on their feathers, and the length of the ridge is kind of like your path length difference. So in a green area of a peacock feather, I have ridges that cause constructive interference for green light and destructive interferences for the other light. So pretty cool. So even though it's not exactly thin film interference, it's pretty much the same sort of idea. I'm getting light wave interference, constructive and destructive, and so I just see different colors. Awesome. Now, the film doesn't have to be a film, right? It doesn't have to be oil. It doesn't have to be this anti-reflective coating. It could be air. If you think about 2 microscope slides, if you've ever worked with microscope slides, right, they're really thin. And when they're together, right, there's usually like an air gap in between because there's usually some dust there. And so with a microscope slide, you can see areas of constructive and destructive interference based off of the thickness of the air in between the layers. Pretty cool. We could also do this with wedges. So if you take two microscope slides and you put like maybe a piece of paper, right? It's got to be super thin. Remember, thin film interference, the thickness of the film has to be really small. So if I took like a piece of paper and I put it so that it kept my little microscope slides at an angle to each other, I would see different thicknesses, right? And so I'd see alternating bright and dark colored bands. There's also something called Newton's rings, and Newton's rings are also thin film interference because what I have is I have a glass lens. That's a plano convex lens. We're going to talk about lenses next week, I think. It has a little circular lens on a flat plate, and when you look at it, you actually see rings. You see this pattern of light and dark rings, and it is because you have this film of air in between two glass plates. Now what's kind of funny is thin film interference is really kind of a wave property of light, and Newton was actually the first one to discover these, which is why they called it Newton's rings, and he described it in terms of light rays, but it's really a wave property, so that's kind of interesting. All right, I have two questions for your WSQ. Here's the first one. A film with thickness T gives constructive interference for light with a wavelength in the film of lambda film. How much thicker would the film need to be in order to give it destructive interference? Answer that on your WSQ. My next question for you is a calculation. See if you can figure this one out. There's two questions here. I have a thin film of gas with the refractive index of 1.2 and a thin film of oil floating on water. The oil is 1.45 and the water is 1.3. The thickness of both films is a wavelength, exactly one wavelength. So, which one has constructive interference and which one has destructive? So does the gas look bright or dark? And what about the oil? Does it look bright or dark? Answer these on your WSQ, and I'll see you in class.